In this video, I will show you how to completely factor a polynomial with real solutions. So now we've talked about the rational roots theorem, we've talked about Descartes' rule of signs, we've just learned about the upper and lower bounds theorem. So now we'll combine all of those skills to make factoring polynomials easy. We'll spend a few moments reviewing what the rational roots theorem, Descartes' rule of signs, and the upper and lower bounds theorems say, and then we'll do a problem. So recall the rational roots theorem, or the rational zeros theorem, says that if a polynomial p of x has integer coefficients for a sub n, the leading coefficient, and a sub 0, the constant term, not equal to 0, then every rational zero of p is of the form p over q, where p and q are integers, and p is a factor of the constant coefficient, and q is a factor of the leading coefficient. So if we had a polynomial like p of x equals x cubed minus 2x plus 8, we would look at the factors of 8 over the factors of 1, since 1 is the coefficient in front of x cubed. Descartes' rule of signs says that if we look at the sign changes in p of x and p of negative x, we would be able to get a sense of how many positive and negative real zeros we have for a given polynomial. So considering again p of x equals x cubed minus 2x plus 8, this has one sign change, two sign changes in p of x, which would then imply that we could have either, for positive zeros, we could have either 2 or an even whole number less than that. So we could have 2 or 0. If we plugged in negative x, p of negative x would equal negative x cubed plus 2x plus 8. And since that has just one sign change, for negative zeros we would expect 1, and that's it. So we would definitely expect to get negative real 0. And the upper and lower bounds theorem says that if we have some linear term, something that might be a factor of a polynomial p, and divide that into p, if we end up in the bottom row of synthetic division, if we end up having all positive terms, in other words, all non-negative terms, in the bottom row after we've finished doing synthetic division, then that number b is an upper bound for the real zeros of p. Similarly, if we divide p of x by x minus a for a less than 0, using synthetic division, and the row that contains the quotient and remainder has entries that are alternately non-positive and non-negative, then a is a lower bound for the real zeros of p. So the rational roots theorem helps us find possible zeros, helps us get a place to begin. Descartes' rule of signs tells us how many positive and negative zeros we should expect. And the upper and lower bounds theorem helps us clear out some of the clutter, as it were. Okay, so let's factor completely p of x equals 2x to the 5th plus 5x to the 4th minus 8x cubed minus 14x squared plus 6x plus 9. We should begin with the rational roots theorem. So we'll look at all the factors of 9, which those are just plus or minus 1, plus or minus 3, and plus or minus 9. And the factors of 2, that should be a 9. The factors of 2 are just plus or minus 1 and plus or minus 2. So now we take each of those factors of 9 and put them over the factors of 2, which will give us the list possible rational zeros of p, possible rational zeros are plus or minus 1/2, plus or minus 1, plus or minus 3/2, plus or minus 3, plus or minus 9/2, and plus or minus 9. Okay, so we've just done rational roots theorem, and we have now a better sense of what zeros we might actually have. Okay, so now let's use Descartes' rule of signs. So first we're looking at just positive p of x to help us determine the number of positive real zeros we might have. So we have one sign change, two sign changes. So positive zeros, we should expect 2 or 0. Now if we plug in p of negative x, we should have a negative 2x to the 5th plus 5x to the fourth plus 8x cubed minus 14x squared minus 6x plus 9. Now we have one sign change, two sign changes, and three sign changes. So negative zeros, we should expect 3 or 1. So altogether, we should have zeros. We should have 5, 3, or 1 real zeros. Now, I'll give it away. We're going to have 5 real zeros here, but now we have a sense of how many to expect that are both positive and negative. So now we have a sense of what possible zeros we might have and how many positive and negative zeros we might have. So now we should start testing values. I propose that we begin with 1. I think 1 is always a good number to begin with. And we could use the remainder theorem to see that p of 1 equals 0. So we should expect that 1 is going to be a 0 by remainder theorem. So now we can do synthetic division. So 2, 5, negative 8, negative 14, 6, and 9. 2 drops down. Then we have 2, 7, 7, negative 1, negative 1, negative 15, negative 15, negative 9, negative 9, and 0. So x equals 1 does confirm x equals 1 is a 0, which means that x minus 1 is a factor. And you all will remember that if we plug in our x's starting 1 power lower than we began with our original p, we get a new polynomial. That's p squared, x minus 9. So p of x equals x minus 1 times 2x to the fourth plus 7x cubed minus x squared minus 15x minus 9. Whew. Okay, so we factored out something out of our polynomial. So now you'll notice that we again have a 2 as our leading coefficient of this new polynomial, and we've got a 9 as the constant term of that polynomial as well. So we should have the same, roughly the same list of possible rational zeros. So now let's move up to 3 halves. So if we try p of 3 halves, just so we don't do synthetic division without knowing whether or not it's a 0, we will, actually with this one as well, get 0 by the remainder theorem. Okay, so now we should do the division. So we have 3 halves, and then 2, 7, negative 1, negative 15, and negative 9. So now we're using our new polynomial after we've factored out x minus 1. Okay, so we drop down the 2. 2 times 3 halves is 3. We got 10, 15, 14, 21, 6, 9, and 0. So this implies that x equals 3 halves is a 0, and x minus 3 halves is a factor. Now another thing to notice here is that we have positive, 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 positive. So we have all of these positive terms in the bottom row after we've completed synthetic division. This implies that x equals 3 halves is an upper bound for the real zeros of p. And now we'll rewrite the polynomial. P of x equals x minus 1, x minus 3 halves, 2x cubed plus 10x squared plus 14x plus 6. Now just to make this a little bit simpler, we can notice that we can factor out a 2 here, and that'll actually eliminate this 2, the fractional 2 in the second factor, so we can rewrite as x minus 1, 2x minus 3, x cubed plus 5x squared plus 7x plus 3. Okay, and now at this point, I would say we can actually just perform Descartes' rule of signs again with this new polynomial here. this new polynomial. So if we do the rational roots theorem again, we have a leading coefficient of 1, constant term of 3, so that means that all we'd have is plus or minus 1 or plus or minus 3. But by Descartes' rule of signs, we notice that there are no sign changes for this polynomial here, so that means that there will be 0 positive zeros, which means it can only be -1 and -3 left. So it's useful to confirm that this is true. I'll just do once for -1. So we have -1, and our remaining polynomial is 1, 5, 7, and 3, which the 1 times -1 times 1 is -1. 5 plus -1 is 4. -4, 3, -3, and 0. So that one works. We have p of x equals x minus 1, 2x minus 3, x plus 1, and then x squared plus 4x plus 3. All right, and the last thing, we can see that x squared plus 4x plus 3 is easily factorable into x minus 1, 2x minus 3, x plus 1, we have an x plus 3, and an x plus 1. So we actually have a 0 of multiplicity 2 here, concluding that x minus 1, 2x minus 3, x plus 1 squared, and x plus 3 is the completely factored form of our polynomial p of x. So altogether, we started by using the rational root theorem and the Descartes rule of signs to get us thinking about what we should expect. We then used the upper and lower bounds theorem in conjunction with synthetic division to help us eliminate some of the clutter. As we used synthetic division, we were factoring out factors in the polynomial p, so we were able to simplify the polynomial a little bit each time, ending up in a place where we found out that there could only be negative zeros left with only 2 possible negative zeros, and we concluded that with a simple factorization of a quadratic polynomial. Though it seems tedious, I'm just taking a lot of time to explain all the parts to make sure that you understand what's going on. As you do this, it will become more intuitive, and hopefully it means that we'll go faster. Pretty cool that we just factored a polynomial of degree 5 completely.